Okay, I have taken this ATR stereo tape machine and connected its two outputs to an oscilloscope. So on the patch bay here we have the output of the stereo output of the ATR tape machine, and that's patched into the oscilloscope. The oscilloscope appears on our patch bay here. The patch bay points go to these two leads that plug into the oscilloscope. You could just as easily have leads, individual leads coming out of the oscilloscope and patch those into the tape machine. But because the oscilloscope is a standard part of our control room, we have it built into the patch bay for convenience. The two traces on the oscilloscope independently show the outputs of the left and right channel of this machine. So I'm going to knock this machine out of azimuth rather badly so that you can see the effect of the machine being out of azimuth on the oscilloscope. I'm going to play the alignment tape here.
AES equalization. 1 kilohertz.
And you can see that the two traces of the left and right on the oscilloscope are not synchronous. They don't superimpose on each other. Now I'm going to adjust the azimuth of the playback head using this hex key here until those two traces look to my eye to be superimposed. Now it doesn't matter if I'm exactly accurate at this stage, because I'm going to be doing a finer azimuth adjustment using a higher frequency. If you think of the waveform as pulses of magnetism on the tape, the lower the frequency, the physically farther apart those pulses would appear on the tape. So as this is a 1 kilohertz tone that we're playing back now, there would be 1,000 of those pulses for every 30 inches of tape, and if I go up a decade from there to 10 kilohertz, then we'll have 10 times as many pulses per unit of tape travel. So the azimuth accuracy of a 10 kilohertz playback will be much, much greater. And I can use the time constant on the scope to show me the 10 kilohertz waveform at the same resolution. And I'll show you what I mean by that. So I'll play back the 10 kilohertz tone, which comes up somewhere here on the tape.
10 kilohertz.
Now, you can see how those waveforms are much closer together. If I adjust the time constant on the oscilloscope, you can now see that we have approximately the same resolution on the waveform. And if I use the hex key, I can now very finely tune in the azimuth so that those two waveforms are superimposed. Now you'll notice there's a small amount of jitter there where the waveform is dithering forward and backward, and that is because this is a mechanical transport, and it's difficult for it to maintain rigid alignment as all the parts are moving. So there's always going to be some small amount of dither in the playback, and what I'm trying to do using the oscilloscope is to center the error so that there is as much leading as lagging in the waveform, and so that on average the waveforms will be superimposed on each other, and I'm minimizing the error at all points. So I now consider the playback head on this machine to have its azimuth properly aligned.